In this video, we're going to cover section 4.6, integration by substitution. There are a few key skills here. So essentially, integration by substitution is the opposite of the chain rule. So remember when we took the derivative of something like sine of x squared plus 3x plus 4, we'd take the derivative of the outer function, which was cosine of x squared plus 3x plus 4, and then would multiply by the derivative of the inner function, which was 2x plus 3. So to take the integral of this function now and get back to the original sine of x squared plus 3x plus 4, we have to make sure that these parts are all in place. So we're going to do pattern recognition first, and then we're going to do a change of variables to find an indefinite integral. So these are just the general antiderivatives. Then we're going to use the general power rule for integration. Then we're going to do change of variables we'll look at a definite integral. And this last one, if it's an even or an odd function, sometimes there are some shortcuts we can use there. So pattern recognition, theorem 4.15, antidifferentiation of a composite function. Okay, so let G be a function whose range is an interval I, and let f be a function that is continuous on I. If G is differentiable on its domain and f is an antiderivative of f on I, then here's what we have. F of g of x times g prime of x equals the antiderivative of g of x plus c. So this may seem a little confusing at first, but if we look at this example we just did over here, this helps us out. So the f part was the cosine. The g of x is x squared plus 3x plus 4. G prime of x is the 2x plus 3. So if you have a composite function, a function within a function, and it multiplies by the derivative, then the antiderivative, or the integral of this, is just the original function, sine of x squared plus 3x plus 4 plus c. So the key part here is we need to make sure that what came or what would have come from the chain rule, taking the derivative, is here in place so that when we take the integral, this is used up in that process and we get back to the original function. We'll do some practice. Here's just the generic. If we use u, which we will do a lot, then we just have f of u du equals the capital F of u, the antiderivative of u plus c. Okay. Now, it does not tell us how to distinguish these, so this is part of recognizing patterns. Okay, so it takes experience being familiar with derivatives. So example 1, recognizing the f of g of x times g prime of x. So here we have a function within another function. Now, so we have f of g of x times g prime of x. Okay, so if we look at this, f of x equals x squared. G of x equals x squared plus 1. And g prime of x equals 2x, the derivative. So we have all of these parts. We have f of g of x and we have g prime of x. So we can take the integral of that. Now, what I would like to do is to do this using u substitution and show you how that works, because this is more commonly used. So we're just going to say u is that inner function, and then I'm going to immediately take the derivative. So the derivative of u with respect to x equals 2x. Now, as we saw above, this says du. That means I'm going to multiply both sides by dx. So the du I'm actually working with will be 2x dx. Okay. Now when I do that in the future, I'm just going to write the dx on the right side. But note that's where it came from. because we took the derivative of u with respect to x. That's our notation. And I can separate that and bring that over here by multiplication. So now I'm going to substitute this in. I have u squared times 2x dx is du, so I just have du. So the antiderivative of u squared is u cubed over 3 plus c. And then at the end, for this general antiderivative, I'm going to put our u back in. So I've got x squared plus 1 cubed over 3 plus c. And there is my derivative. Again, if you recognize that, you can kind of jump to that. I like the u process just because it kind of gives us a more concrete way, and it'll give us enough practice when it gets more difficult and we need that u. It helps us out having practiced it already. The key part is the u is the inner function. So at example 2, what is the inner function? Well, I think u is going to equal 5x. So du equals 5 dx. Notice again the dx would be under the du, but I just rewrote it in the middle. So I'm going to rewrite this. So I've got e to the u, and then my 5 and dx together give me the du. So this is e to the u plus c. So that's e to the 5x plus c. Now, these patterns fitted exactly, so it was fairly obvious to see. Sometimes, though, we might have a constant multiplier that doesn't belong there, so we pull it out. And this is where the u can help us keep track of what exactly needs to be in there. So let's take a look. So find the indefinite integral. Again, I'm going to use the u substitution, is what it's called. U substitution, so u equals the inner function is x squared plus 1. Du equals 2x dx. So I've got my x squared plus 1 part, so I've got u squared. And then here I've got x dx, but I don't have a 2. So what I do is I say, I'm going to divide this by 2, so I've got du over 2. Okay, there's another way you can look at this. So what I did is I solved for the x dx because that's what I'm substituting in for. So x dx equals du divided by 2. So since I had x dx, I substituted in du divided by 2. The other way we can look at this is if I have u squared times, we'll just put our x dx there back. I need to get that 2x dx. So what I'm going to do is I'm going to times by 2 here, and I'm going to multiply by 1/2 out here. Okay, that gives me the 2x dx, so that gives me du, and I've got this 1/2. Either way, we're going to come up with the same thing. So that would be 1/2 the integral of u squared du. So that's u cubed over 3 times 1/2 will make that 6 plus c, and we'll substitute in that what u was, x squared plus 1 cubed divided by 6 plus c. Now please note this only works for constants. I can't multiply by an x and then divide by a 1 over x on the outside because constants are the only numbers that we can pull out. So this only works if we're dealing with that number or a number that we could pull out. These exploration will be good to do. We will probably talk about these in class together. But again, these will fit. And what again I would do is I would say you figure out what is the inner function. Okay. And then take the derivative, and that would be part of what is. So on the first one, u would be x to the 5th plus 1. So du is 5x to the 4th dx. So again, we've got the 5x to the 4th dx. There's our du, and there's our u. On this last one, we'd have to show how we multiply and divide by a constant. So here again, I would go u is 5x plus 1. Du equals 5x to the 4th dx. So I would go x to the fourth dx, which is what I have in there, is du over 5. Okay, and doing this way helps us on some problems that are even a little bit more complicated. It's a good warm-up to that process. So change of variables is kind of what we've been practicing already. We completely rewrite it as f of u du. And so let's do some more examples. Again, this usually takes pattern recognition, it takes experience, it takes time, so it requires us to do a lot of these problems. Again, u is the inner function, so I'm going to say that's 2x minus 1, du equals 2 dx. Now, I've got the integral of the square root, that's actually right, u to the 1/2, but I just have a dx, so I'm going to solve for dx, again, get what I have in there alone, and that's going to tell me what I substitute in for dx. So I've got du divided by 2. Again, you could reason this out, you could think through that process, but if we do these calculations, it's just algorithmic and we don't have to second guess ourselves or try to figure it out. So this would be u to the 3/2. I'm going to put that 1/2 over 3/2 plus c. So if I do multiply by the reciprocal on the 3/2, my 2's will cancel out. So I've got u to the 3/2 over 3 plus c. Now, because it's an indefinite integral, we should put our u back in. So 2x minus 1 raised to the 3/2 over 3 plus c will be our final antiderivative of our original function. Let's take a look at this one. So this is similar to the last one, but it is not quite the same because we have an x. So this is where the u becomes essential. So I've got 2x plus 1, du equals 2 dx. Now I just have a dx here, but I've also got this x. So I need to write this in terms of u. So I've got some x times u to the 1/2 times, we'll put that du over 2 back in. If you do u substitution and substitute our u back in, our du back in, and you still have an x, we have to get rid of that x. So what we do is we look at this equation here and we solve this for x. So I know u equals 2x minus 1. The question is, what does x equal? So I'm going to add 1 to both sides and divide by 2, and x actually equals u plus 1 over 2. So now I've got u plus 1 over 2 times u to the 1/2 divided by 2 du. And now we are going to attempt to take the integral of this. Okay, and it'll just be a little bit of our antiderivative work. I'm going to pull these 2 times 2 on the bottom is 1/4. U times u to the 1/2 is u to the 3/2 plus u to the 1/2 du. So now we've rewritten. Here I've got 2 functions that are added, so I can do that easily. So I'm going to go u to the 5/2 divided by 5/2 plus u to the 3/2, again adding 1, and then you just put it over. I like to do that straightforward that way and then deal with the 1/4 on the outside. Okay. When I do this, I'm going to get u to the 5/2. The 2 will cancel out when I multiply by the reciprocal. Multiply by 2/5. 2 and 4 will simplify, so I believe that's over 10 plus u to the 3/2. The 2's cancel, so 2 times 3 is 6 plus c. Our final step will be to substitute u back in. 2x minus 1 to the 5/2 over 10 plus, sorry, I was going to put something else. All right, 2x minus 1 raised to the 3/2 over 6 plus c. And there's the antiderivative from change of variables. All right, let's look at example 6. Now this one might be a little bit trickier. I've got sine squared of 3x cosine of 3x dx. We kind of have three different functions here. I've got four different functions, maybe. I've got something squared. I have sine of something. I have 3x. And I have cosine of something. So let's take a look. Sometimes when I do problems, I will choose a u, take the derivative of it, and realize I have too much left, and I have to choose a different u. In this case, I'm going to assume my outer function was something squared, so my inner function is going to be sine of 3x, okay, because we have sine of 3x squared here. So my du will be cosine of 3x dx. No, sorry. I've got cosine of 3x times 3 dx. Okay. So I've got my sine of 3x. Rewriting this, I've got u squared times, let's see, I have almost all of du, but I'm missing a 3. So I want to get rid of this 3, and then it'll match. So I'm going to divide by 3. So I've got du divided by 3. That would be u cubed over 9, because I've got this 3, and then I've got the 3 that would be brought down doing the product, doing the exponent rule for antiderivatives. So this would be, let's say, sine cubed of 3x over 9 plus c. Again, we are going to need to practice this u change of variables because it comes easier as you have done more problems and you get more experience. So here's some guidelines for making the change of variables. Let's see, make sure we understand and are following these. So we choose a substitution. Usually it's best to choose the inner part. So it's the inner function. We compute du, which is g prime dx. We rewrite the integral in terms of the variable u. Again, this is where we might need to figure out what our du equals and adjust, as we did on the previous one. We divided by 3. Then we find the resulting integral, replace it back in, and we can check our answer by differentiation. Theorem 416, the general power rule for integration. So we've already seen the power rule for integration. If you have x to some power n dx, that would be x to the n plus 1 over n plus 1 plus c. Okay, that's the general power rule. Sorry, that's the power rule for integration. General just means, hey, perhaps we're dealing with a function within a function. And so here we have what we saw at the beginning. If we have something raised to an exponent times its derivative dx, then we can just take it back. And here it is written, instead of f and g, it's just with u, kind of the change of variable practice. Okay, so this substitution general power rule, this is just asking us to do this using the general power rule. So here I've got 3x minus 1. I'm going to write real quick just to check and make sure, yep, I've got my du here. So this would be u to the 5th power divided by 5 plus c. And that's it. Okay. Here I've got e to the x plus x would be my u. So du would be e to the x plus 1 dx, which is what I have. So I can just take this and say, hey, I've got my u squared divided by 2. So e to the x plus x squared over 2 plus c. Here, there's my u. My du would be 3x squared dx. So I'm just going to take that. That's the integral of u to the 1/2 du. So that is going to be x cubed minus 2 raised to the 3/2 power divided by 3/2 plus c. And we could rewrite this as 2/3 multiplied by the reciprocal. That would be the most this appropriate thing to do here. Now here we've got a negative exponent, but it's the same. Let's rewrite this though just to check. Negative 4x times 1 minus 2x squared to the negative second power. Okay, so here's my u. My du would be negative 4x dx. So I do have the integral of u to the negative second power du. So I'm going to add 1 and have it over that. U to the m plus 1 over m plus 1 plus c. So I've got negative 1 over my u, 1 minus 2x squared plus c. E, cosine squared of x, sine of x. So my u is going to be cosine of x. My du will be negative sine of x dx. So I've got this negative I've got to pull out here. Then I have u squared du. So this is negative cosine of x cubed over 3 plus c. Theorem 417, change of variables for definite integrals. So now what we're going to do is we're going to find the definite integral. Again, that just means we're calculating the number, which could be represented by an area under a curve. And so if we have this from a to b, what we'll do is we can find the antiderivative like we normally would, and then we just put a and b into that inner function. And there are two ways to do this. This Theorem 417 is one of them. The other is just you find the antiderivative and plug it in. Sometimes one is easier than the other, but usually it's not too bad. So let's do this. Use substitution. So that's x squared plus 1 du equals 2x dx. So here I've got x dx. So I'm going to divide both sides by 2 again. So I'm going to rewrite this as u cubed du divided by 2. Now the problem is I cannot just put 0 and 1 here because 0 into u is not the same thing as 0 into x. That's the key here. And so what Theorem 417 told us was that take this 0 and put it into u and put its resulting answer here. So 0 squared plus 1 is 1. And then 1 squared plus 1 is 2. So I put both of these in and I put the resulting number here on the integral. Now I can take the integral, so that's u to the 4th divided by 4 plus c. Oh, doing definite integrals, so we're not going to use the plus c. Evaluated from 1 to 2. Apologize those of you who caught I dropped my 1/2, my 2 here. So I've got 1/2 times u to the 4th over 4 evaluated from 1 to 2. So this is 1/2 times, let's see, 2 to the 4th is 16 divided by 4, so that's 4, minus 1/2 times 1/4, so this is 2 minus 1/8, and I believe that's 15/8 would be my answer. Okay, so that is doing this change of variable process, evaluating this definite integral by using 4.17. The other way to do it, and again, they're equivalent, sometimes one's easier than the other, is to, at this point, you go back and I'm going to write x squared plus 1 to the 4th power over 8 and evaluate this at the original ones. So if you plug what u equals back in and you're back in terms of x, use the initial limits of integration. If I put a 1 in here, I'll get 2 to the 4th divided by 8. If I put a 0 in here, I'll get minus 1/8. So 2 to the 4th divided by 8 is 2 minus 1/8 is 15/8. Either way works. And I do both. I usually don't have a strong preference that I can think of. Sometimes I'll just substitute it back in. Sometimes it is easier to put these values in. Then you're dealing with simpler calculations later. All right, example 9. I'm going to rewrite this here as x times 2x minus 1 to the negative 1/2 power dx. So my u is 2x minus 1. My du would be 2 dx. So I already know I'm going to have to substitute in du over 2 for dx. So I've got x times u to the negative 1/2 times du divided by 2. Here again we have this x that we'll have to substitute that in. So that's u plus 1 divided by 2. This seems similar, the same as what we did before. So I might actually just jump to that antiderivative we found. No, it is slightly different, I think. The u is the same, but it was not a negative 1/2. So let's substitute this back in. The integral of u plus 1 over 2 times u to the negative 1/2 times du divided by 2. So I've just taken each of these parts here and the x we substituted in. So that gives me, I'm going to pull out the 1/4 times the integral. Sometimes I leave my indices off so I don't have to copy them every time. And that gives me u to the 1/2 plus u to the negative 1/2 du. So let's plug in our u values, or find our new limit. So if I plug in 1 here, 2 times 1 minus 1 is 1. If I plug my 5 in here, I have 2 times 5 minus 1 is 9. Okay, so now I'm going to go 1/4 times u to the 3/2 divided by 3/2, or multiplying by 2/3, plus u to the 1/2 divided by 1/2, or multiplying by 2, evaluated from 1 to 9. So let's just see what this comes out to be. So 1/4 times 2/3 times 9 raised to the 3/2 plus 1/4 times 2 over 1 times 9 raised to the 1/2, and then we will subtract the same thing with 1. Sorry, this should be a 3 here, 2/3, minus 1/4 times 2/3 times 1 minus, since I didn't use parentheses, I'll subtract both of these, 1/4 times 2 times 1. So this should be minus 1/6 minus 1/2. These will combine and actually become negative 2/3. And then here, my 2's cancel, so I've got 27/6 plus 3/2. 27/6 plus 3/2, this would be 9/6 equals actually 6 minus 2/3, 5 1/3, or 16/3. Okay. Now I've done this problem. I look at what the book did. The book actually said u equal to the square root of 2x minus 1. So I want to show just the first part of this so that you can see this. We're still going to take we're still going to find dx, but in a slightly different way. Change colors here so you can see. We're going to square both sides. So u squared equals 2x minus 1. So u squared plus 1 over 2 equals x. And then I'm going to find dx here to substitute it back in. So what's the derivative of this? That would be, that will be, looks like u du, because it would be 2u, but that's divided by the 2. This part goes to 0. So then we could substitute this back in. And I've got three parts. I've got the u on the bottom, I've got the x and the dx. So the u on the bottom times the value of x times dx. My u's cancel, and I'm now taking the integral of u squared plus 1 over 2 du. Now, if you do this, we'd change our limits of integration. So when I plug 1 in here, I'm going to get 1. Plugging 5 in here, square root of 2 times 5 minus 1 is 3. I'm going to get the same answer. And that one is easier. I didn't see it. I was just going with the inner function. But as we saw there, it was perhaps fewer algebraic steps to let u equal the square root of 2x minus 1. All right, let's talk about the patterns of integration of even and odd functions. So integration can still be difficult. Occasionally, you can simplify the evaluation by looking at symmetry. So remember, even function is symmetrical across the y-axis. Odd function is symmetrical around the origin. Okay? So in both of these cases, we look at an integral going from a negative constant to a positive constant. To simplify this for an even function, we'll notice that it's twice as big as going from 0 to a. Okay, so what we'll do is we'll just find half of the area and then we'll double it because we know it's symmetrical about the y-axis. The nice thing is if it's an odd function, goes from negative a to a, then this equals 0 because they will cancel each other out. There will be as much positive area as there is negative area. So example 10. We see that we're set up to use this if this is an even or odd function. Let's just review how do we determine or verify if it's an even or odd function. If I put in a negative value to an even function, then I will get the original function back. If I put a negative value into, let's change that to g. If I put a negative value into an odd function, then I will get the exact opposite. So I'm going to put a negative value in for x here, and if I get negative sine cubed of x cosine of x minus sine of x cosine of x, then it's odd. If I get this exact function back, then it's even. So sine cubed of negative x cosine of x plus, cosine of negative x plus sine of negative x times cosine of negative x. Let's evaluate that. Now to remember that, we need to remember is sine and cosine which are even and which are odd. To assist us, if you remember the graphs, cosine looks like this, except it's more centered there. And sine graph looks like this. So just by remembering the graphs, this cosine is even and sine is odd. So that means cosine of negative x is actually just equivalent to cosine of positive x, and sine of negative x becomes negative sine of x. And because we're cubed, that negative will come out. So yes, it's an odd function because it's going from the same constant. This equals 0. And that finishes our notes for section 4.6, integration by substitution. Thank you for watching.